Hi, welcome to this short lecture on deadlocks and system recovery. In this lecture, we will be looking at the concepts of deadlocks, okay, to understand what they are and how they can actually impact a system in the context of a real-time system that we are studying. And then we will also look at within the context of a microcontroller, what are watchdog timers, okay, and how they can actually help us in system recovery. And we're also going to explore another feature known as the brownout, okay, to see how they can help in ensuring that we have a safe and a reliable system working all the time. So the first thing is deadlock. Okay, so what is a deadlock? A deadlock is basically a situation where you have two or more threads, okay, waiting for each other's resources. Okay, so as you can see, that means both the resources are shared. Okay, and it only occurs if the threads require the shared resources simultaneously. Okay, so in the example that you're going to see, we have two tasks, T1 and T2, and both of them require two resources, R1 and R2, simultaneously in order to function. Okay, so let's look at this situation here. So in this uh, timeline, you can see that at time t equals to 0, what we have is T1 is running, okay, and while T1 is running, uh, it acquires a resource R1. Okay, so at this point in time, R1 has been acquired. So when you say R1, it could be a mutex, it could be a semaphore. So thread 1, since it was running first, it had the opportunity to acquire this resource. Okay, and at this particular instance of time, before it could finish whatever it was doing and release the resource, before that could happen, it was blocked. Okay, so something happened here. It could have been a trigger because of a ISR that took something that blocked this T1 from proceeding. Okay, so at this point of time, okay, because T1 was blocked, uh, the OS switches over to task 2. Okay, so task 2 is running, and when task 2 is running, task 2 has a chance to acquire another resource, which is R2. Okay, so at this point of time, it acquires resource R2. Okay, and what then happens is it then attempts to acquire resource R1 here. Okay, by trying to get this resource, but since resource R1 was already taken by thread T1, you can see that it is not getting the resource. Okay, it's not uh, able to get the resource, and so what happens, it goes to a block state. Okay, so at this point onward, it goes to a block state. Okay, so blocked or pending, okay, is interchangeable terms. So it goes to a block state waiting for resource R1, and since it goes to a block state, okay, uh, at this point of time, it also happens that thread T1 changes, okay, to a ready state, and T1 then switches over to a run state here. And when that happens, okay, T1 resumes, okay, running from this point onwards, and later on, so at this point of time, we must remember that T1, okay, still holds R1, okay, and T2 is already holding R2. So at this point of time, T2 holds, okay, R2, and when T1 starts to resume, okay, and at some point of time, it then tries to acquire resource 2. Okay, it tries to acquire resource 2, and then it gets blocked. Okay, why? Because T2 is still holding on to it. Okay, since it gets blocked, it goes to a pending state or a block state. And what happens after that? Okay, you will see that both T1 and T2 from this point of time onwards, okay, they are both blocked indefinitely. Okay, why? Because T1 is blocked waiting for a resource that T2 is having, and T2 is blocked waiting for a resource that T1 is having. Okay, so at this point of time onwards, basically neither task 1 or task 2 will be able to proceed. Okay, so that is what you call a deadlock situation. Okay, because both of these tasks are waiting for resources that the other person has. Okay, and neither one is going to give them up. Okay, so this is a deadlock situation, a classic one, in fact. And as you can see, this is only based on 2 threads. Okay, and it's also possible for multiple threads. If you extend the idea, you can have many threads, okay, in a potential deadlock situation when there are multiple shared resources. Okay, so imagine 3 resources, 4 resources, and at the same time 3 or 4 tasks, and everybody wants these resources, okay, to proceed. Okay, and that could lead to even a bigger deadlock situation. Okay, the good part is there are development tools that exist that can actually do some software analysis, okay, to preemptively tell us if there are some possibility of deadlocks within the code that we have written. Okay, so some of the IDE tools, okay, by manufacturers are quite advanced to give us some of this software analysis. Okay, but as always, it is still up to the programmer, okay, to make sure that we find a solution. And of course, the best way is to even prevent deadlocks from even happening in the first place. Okay, so how do we go about preventing deadlocks from happening? So basically, there are 2 approaches to this. Firstly is we require all threads to acquire resources in the same order. Okay, so for example, if task 1 and task 2, okay, both of them require R1 and R2, then I must enforce the order that I must first take R1 followed by R2. Okay, and if I go back to the earlier example here, if T1 is running, okay, and if T1 runs and it requires R1 first, and after that it goes to a so it requires R1 first, and after that it goes to a block state. And if T2 runs from here and then it tries to acquire resource 1, it will automatically get blocked. Okay, it will automatically get blocked, allowing a chance for T2 to resume. Okay, so effectively, if I enforce the order, whoever is the first person to lock the first resource will basically ensure that he will eventually get all the resources subsequently, one after another, until he finishes everything and releases the resources. Okay, so by enforcing the order in which resources are acquired, I can ensure that deadlocks will not happen, because any other task that also wants these shared resources will have to wait until the first task that acquired the first resource releases everything. Okay, of course, the drawback would be in some of these cases we may end up locking resources longer than necessary. Okay, so again, maybe at this point of time R1 is not needed, but because R1 is part of the whole package of resources that I need, I will want to acquire it upfront. Okay, and sometimes there is also no particular order that may seem convenient for all the threads. Okay, so sometimes the resources may be tied to different activities, okay, that a task may be doing. So it is a bit of a challenge sometimes figuring out if it's possible for all resources to be actually acquired upfront. And so that is one approach. Okay, you sort of enforce an order. And the second approach is this, where we sort of have a mechanism so that if a thread realizes that any one resource cannot be acquired, then I must release all the resources and start over. Okay, of course, this may or may not always solve the problem, because then you also need to make sure that when they start over, they don't end up in the same sequence again, then again leads to another deadlock situation. Correct. So the first option here is a better option in enforcing that deadlocks actually do not occur, okay, by sort of putting in place a sequence of resource acquiring. Okay, so that is basically deadlocks. Okay, so deadlocks are quite serious, okay, because if your deadlocks come into a system, okay, they will be able to hang or basically put multiple tasks in a sort of hung state for an indefinite period of time. Okay, so it is important that we analyze our code, analyze our resources to see if such a potential situation can occur. Okay, now we're going to look at this peripheral block that most microcontrollers have, known as Watchdog Timers. Okay, and what is a Watchdog Timer? Is basically a separate hardware counter. Okay, so if you recall in your Arduino Uno or your Atmel 328, okay, you do have timer blocks. Okay, you have timer 0, timer 1, and timer 2. Okay, so these are all specialized hardware timers, okay, that we have used uh, in EPP and so on for our PWM generation, okay, and doing some uh, interrupt based counting. Okay, similarly, a watchdog timer is also a separate uh, a hardware block. Okay, and it's basically a counter, and the objective of this counter is to count down to 0 at a fixed rate. Okay, so basically the timer, okay, assuming it is a 8-bit timer, so I will start at maybe 1 and then I count down all the way until I hit 0. Okay, and the main objective of using this timer is I must not let this happen, or I do not want this to happen. That means I do not want it to reach 0, because if it reaches 0, then we say that a failure has occurred in the system. So what I must do is I must continuously go in, and before it reaches the end, issue a reset. Okay, so that it goes back to the start and counts again. Okay, so the software in our application is expected to periodically restart the counter so that it never goes to 0. Okay, if there's ever a situation where the watchdog timer goes to 0, then we can say that a failure has occurred. Okay, that means we were not able to do this activity, this periodic reset. Okay, so something has gone wrong, so that is why a watchdog uh, hitting a 0 is deemed as a failure. And usually what happens in general microcontrollers, we can say that a watchdog hardware has the ability to send a reset signal to the CPU. Okay, so most microcontrollers have the ability to uh, automatically generate a reset signal. Okay, automatically generate a sort of reset pulse, okay, to the microcontroller the moment you hit a countdown to 0. Okay, so the reason why you want to do that is uh, again, once it hits 0, we have to assume that something has really gone wrong. Okay, so the best way to recover the whole system is to do a hardware reset. Okay, of course, in some safety critical applications, okay, uh, you must also ensure that you put everything into a safe state. Okay, before you reboot the whole system. Okay, because your hardware or your application, your device may be doing something that is critical, that involves safety, okay, or some very dangerous operation, and you want to make sure that you sort of put everything into a safe state before you issue a reset. Okay, in multi-threaded applications, okay, like OS based systems, it's important that you verify more than just that the fact that the CPU is executing instructions. Okay, when we say that we have a periodic software loop here, okay, and you are not able to run it, then it could be that your CPU is not able to execute instructions. Okay, but in a real-time system, the the periodic loop that is supposed to be resetting the timer could still be functioning, okay, even though I may be in a situation of a deadlock or priority inversion. Okay, so if you recall deadlock and priority inversion, basically in both these cases a few threads are affected, but the whole system may not be compromised. Okay, so it could be that the CPU is still functioning, okay, but a few tasks are in a deadlock situation or in a priority inversion situation, but this periodic timer to go and reset the watchdog may still be functioning. Okay, so just because we have a watchdog timer doesn't mean it can help detect all of these problems. Okay, but it can help to detect a major failure where the CPU cannot execute code anymore. Okay, but in a situation where deadlocks can be possible, or priority inversions could be possible, we still need to implement other strategies. Okay, that means we may still need to factor in maybe the computational time of the task, whether we have been able to fulfill the deadlines, okay, for each of the tasks in the system, to see if there is something going wrong. Okay, so all of these are strategies, okay, that you need to sort of implement together with the watchdog to make sure that you try to catch as many of the possible things that can go wrong within the system. Okay, so basically what we want is you want to prevent runaway code, okay, in the system. And important thing to note is the timer operates independent of the CPU, and it's also independent of the clock of the microcontroller unit. Okay, uh, as we know, the Arduino uh, has multiple clocking options, and the one by default our Uno board has is actually the 16 megahertz. Okay, but different boards may have different clock frequencies, and you may also choose other internal clocks to run your microcontroller on. But the Watchdog timer has its own independent clock. So the Watchdog timer itself, okay, has its own independent clock source that is separate, okay, from the one that Arduino is the main microcontroller is using. Okay, so as long as I make feed it a watchdog reset, okay, before the periodic timeout, then I'm safe. Okay, on the Arduino Uno, this clock here, this uh, separate clock is running on 128 kilohertz, okay, and it has a 4-bit prescaler, okay, to decide the frequency at which the timer or the counter is actually decrementing. Okay, what I need to do is, again, I need to issue a watchdog timer reset instruction, okay, before I reach the count of 0. Okay, um, in in the Arduino Uno, I have two options of what to do when my counter eventually hits 0. I can either issue an interrupt or I can issue a system reset. Okay, in interrupt, or in fact I can do both at the same time as well. So there are three modes. In the first mode, okay, in interrupt mode, I can say that the watchdog timer gives me an interrupt when the timer expires. Okay, so in this mode, in just pure interrupt mode, this is basically something like your timer 0 interrupt or timer 1 interrupt. Okay, so once it counts down to 0, I issue an interrupt. Okay, so this can be seen as an alternative to using timer 0 or timer 1 or timer 2. And what can it be used for? It can be used as a general system timer. Okay, it can be used to maybe make sure that I do not exceed a maximum time limit for certain operations that I have for a particular task and so on. Okay, so you can use it like a general purpose timer in just pure interrupt mode. The one that is, of course, what we really need is the system reset mode, where the watchdog timer is able to give a reset, okay, when the system timer expires. Okay, so the reason is once we hit this situation, that means we were not able to issue this watchdog timer reset instruction. Okay, so if I'm not able to issue this instruction within the timeout period, then something is wrong. Okay, so we can say that potentially the system is in a hung state. Okay, so I want to issue a system reset. Now the third mode, which is quite interesting and quite useful, is I can do both one after another. That means the moment the watchdog timer hits 0, I first generate an interrupt and then I issue a reset. Okay, why do we want both at the same time? Because like I said earlier, in some embedded applications such as safety critical, or where there's some danger involved, you may want to put the device into a safe state, okay, before you do a shutdown. Okay, so in that case, the interrupt helps me to execute, okay, potentially execute some code, okay, that can allow me to put the system in the safe mode. Okay, but again, this is may or may not work, okay, like I said, because when we say the watchdog timer is triggered, something has gone wrong. Okay, it could be a total timing failure, in a sense that some task was hogging the entire CPU, okay, that the watchdog timer instruction could not be executed. Okay, in that case, when I generate another interrupt, it may be able to execute, okay, but it's not guaranteed, okay, because the system is already in a questionable state. Okay, if my system is already in a situation where the CPU is not even able to execute any code, then even triggering the interrupt is not going to help me in any way. Okay, so this interrupt is going to help us in a situation where I'm still able to execute code, but maybe not within timing specification. That's why the timer triggered. Okay, but I'm still able to jump to interrupt. Okay, interrupt service routine, and put some of my peripherals or devices in a safe state before I issue a system reset. Okay, so this gives me an option, even though we can't really guarantee that the interrupt service routine will actually get to run. Okay, so that is the idea of the interrupt and system reset mode. Okay, so that is how the watchdog timer operation sort of works. In terms of the reset, basically what happens is the moment the watchdog times out, what it will do is it will generate a single clock cycle, clock pulse. Okay, and at the same time I will issue the internal reset. So this is to reset the microcontroller. Okay, so this is to reset the microcontroller. And what do? I hold the reset pin for a T out period. Okay, I hold the reset pin for a T out period, which is basically the same as the timeout period for the watchdog timer to count from the highest value to 0. Okay, once I finish the T out period, then I release the reset line so the controller can now start the reboot process. Okay, in the Arduino Atmel328, basically this is how it looks like internally. You don't need to worry about this hardware and all. This is just for your information only. Okay, so like I said, we have a 128 kilohertz internal oscillator, okay, that is unique to this. There is a watchdog reset line. Okay, as long as I issue the watchdog reset command, it will trigger this line to start the watchdog from its top value again. Again, these are additional bits. We do not need to worry about it, but as we have studied before, these are bits to enable the watchdog and enable the interrupts, okay, if you want to use them. Okay, so watchdog timer is to detect this situation where your CPU could potentially be in a hung state. Now, there is also another hardware sort of protection mechanism that most microcontrollers have, which is known as brownout detection. Okay, and what does it do? It monitors the VCC level during the operation of the device. Okay, as we know, your microcontrollers usually have to have a fixed supply. Okay, in some cases can be 5 volts, in some cases can be 3.3 volts. Okay, whatever is the case, okay, what we have to ensure that this voltage is stable. Okay, if there is some fluctuations in the voltage level, okay, that is supplied to the microcontroller, the operations of the device can be compromised. Okay, so what we want to do is we want to make sure that the voltage doesn't drop below what is acceptable to the controller, that is safe. Okay, and so what we do is when the brownout detection is enabled, and if we see that the VCC decreases, that means from 5 volts, okay, it decreases to a value below the trigger level. So the trigger level is sort of a hysteresis curve because we have a bottom minus and a bottom plus. So if I drop below the V bot minus, okay, so I say this is a 4.1 volt. If I drop below 4.1 volt, then I will issue the brownout reset. Okay, and once I issue the reset, I'll hold it in reset until it climbs back up again above the VBOT plus. Okay, VBOT plus could be again another value, could be V4.9 volts. Okay, once I climb up above the VBOT plus, then I wait until a timeout before I start the reboot process. Okay, so this picture sort of shows it nicely. Okay, as you can see, this is the VCC. So assuming this is 5 volt. Okay, once I drop below VBOT minus here, Okay, let's say this is 4.1 volt. So once I drop below this threshold, I issue the reset. Okay, so I issue the reset here. And then what happens? I hold the reset line until the voltage climbs up again above V baud plus. Okay, so maybe this is 4.8, 4.9, something like that. Okay, once it goes above V baud plus, that means I am back to a safe level. Okay, so I'm back to a safe level. Then I wait, I keep holding the reset line for the duration of T out. Okay, and then I release the reset line. Then the reboot starts. The reboot process starts. Okay, so the whole idea of brownout detection is to uh, detect any drop in the voltages of your supply. Okay, so right now we're going to look at a reentrant function. So this is just an additional set of slides that I added to sort of understand some context of OS. Okay, as we have seen, we can always a context switch can happen anytime. Okay, while multiple threads are running, which means that if I have shared functions, okay, so we have seen the idea of shared data, okay, a common data structure, an array, and so on that is shared between multiple threads. But at the same time, you can write a function that is shared, okay, a piece of code that is shared between multiple threads. Okay, so for example, if I have this function, which is to say store string, okay, in that is used by both thread A and thread B, and at this point of time, I enter thread A. Okay, so I'm already in thread A, and in this point of time I enter the function store string, and before I can finish the function, okay, I have a context switch, and thread B is also going to call the same function. Okay, so this function here, store string, is a common function, okay, that thread A, task A will also access, and task B will also access. Okay, so while task A was sort of doing it halfway, a context switch happened, okay, and I moved over to task B. So task B again will start from the top, and then it will execute again. Okay, and this time now it finishes, and then it goes back to task A, and task A resumes from where it left off. Okay, and carries on. Okay, so in this kind of situation, okay, a function that is shared, okay, how do you ensure that it will still be thread safe? Okay, for shared data, shared variables, we saw the idea of mutex. So if you recall, we can use mutex to lock and unlock. Okay, if I have a shared data structure between two or more tasks. Okay, but for a shared function, what do I need to do? I need to make sure that these are thread safe. That means they must only use thread specific instances of any data. Okay, so that it is not shared with any other threads. Okay, and this is in a sense quite transparent, because as long as I use automatic or dynamic allocation within the function, then no problem. Okay, that means when I go into the function, then I declare variables or I do a malloc, okay, then that is no issue, because then those variables are created only within the function when I enter. Okay, so that becomes thread safe. Okay, the danger comes if I try to use any static or global variables. Okay, because if they are static or global, then they are not thread specific, they are always persistent. Okay, they have a single instance, so I must be careful not to use static or global variables if the task that I am or the function is going to be shared between multiple tasks. Okay, so again, this is just an important thing to note, okay, when you're developing a project that has OS in it, to make sure that the functions themselves are thread safe. Okay, so in summary, okay, so you look at the deadlocks in RTOS design. We talked about Watchdog Timers, okay, and as well as the brownout protection in the microcontrollers. Okay, so again, this is a short lecture just to give you guys the idea on some of these concepts, okay, which are quite essential. Okay, you may not use it specifically for this modules project, but it is still very good to know that these things are critical in RTOS systems. Okay, thank you.